Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 23, 2026, just 3 days ago. It introduces a framework called SWE-Pruner that achieves a 23 to 54% token reduction on agent tasks like SWE bench verified and up to nearly 15 times compression on single-turn tasks with minimal performance impact. The paper is titled SWE-Pruner, Self-Adaptive Context Pruning for Coding Agents. And, as we'll see later, the way it mimics human skimming to filter out noise while retaining critical code structure is really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. To visualize just how significant those savings are, Figure 1 breaks down the efficiency analysis on the SWE bench verified benchmark. The plots compare the base agent in gray against the pruned version in orange, covering both Claude Sonnet 4.5 on the left and GLM 4.6 on the right. You can immediately see how the orange curves shift to the left, which indicates a reduction in resource usage. For Claude Sonnet, prompt tokens drop by 40%, and interestingly, the total agent rounds decrease by about 20%. The gains are even sharper for GLM 4.6, where the number of interaction rounds falls by nearly 35%. Suggesting the agent becomes much more decisive when the noise is removed. Well, to understand the root of the inefficiency, Figure 2 breaks down exactly where the token budget goes during a typical coding task. It displays a donut chart of token consumption split by operation type. The massive dark orange section represents read operations, which devour over 76% of the total tokens. This happens because agents constantly scan full files to map out the codebase. Meanwhile, actual execution and editing, shown in the lighter upper sections, combined account for less than a quarter of the usage, which highlights why targeting those read operations is so critical. So, Figure 3 maps out the solution. The left panel illustrates the interaction workflow, where SWE-Pruner sits as middleware to intercept raw context from the environment. Crucially, the agent sends a goal hint, shown in the top right, which is a specific natural language query describing exactly what it needs. This hint guides a lightweight neural skimmer to perform line-level scoring, which identifies the relevant code lines shown with orange bars. Then, adaptive selection filters the rest, ensuring only the necessary context reaches the agent. Alright, with the pruning mechanism explained, Table 1 quantifies the impact on the SWE bench verified benchmark. The crucial takeaway here is in the success column, where the performance for Claude Sonnet 4.5 remains virtually unchanged, dropping less than half a percentage point. Yet, look at the savings on the far right. The framework slashes token consumption by 23% and cost by nearly 27%. The results for GLM 4.6 in the bottom rows are even more striking, with token usage falling by 38%, proving the agent becomes leaner without losing its edge. Next, Table 4 extends the evaluation to single-turn tasks, specifically long code completion and question answering. The goal here is to maintain performance under strict 4 times and 8 times compression constraints. In the long code completion section on the left, the highlighted bottom row shows that SWE-Pruner maintains an edit similarity of roughly 58, even when compressed 8-fold. This significantly outperforms baselines like LLM Lingua 2. Then, looking at the question answering results on the right, the efficiency gain is even clearer. The framework reaches an effective compression ratio of nearly 15 times, shown in the last column, while maintaining 59% accuracy, proving it can aggressively filter context without losing critical information. Okay, now that we've seen the performance, Figure 6 reveals the architecture that makes it possible. The core is the QN3 re-ranker backbone on the left, with red blocks indicating fine-tuned layers. From there, the workflow splits. The top branch, Path A, manages pruning by feeding multi-layer features into a CRF layer. This CRF, or conditional random field, is a sequence model that tracks dependencies between lines, ensuring the kept code remains syntactically coherent. Finally, Path B at the bottom produces a standard relevance score for the document. Wrapping up, 2 takeaways stand out. SWE-Pruner effectively overcomes the context wall by treating compression as a semantic, goal-driven task rather than a mechanical one. By mimicking how developers skim code, it significantly cuts costs and latency without breaking the logical structure needed for debugging. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.